Thank you, Andrew. So, I'll keep this short. We're at the end of a long day. And in fact, my goal here today to start this panel discussion is I'm not really going to try to get across, I will by necessity insert some of my opinion. But what I'd like to do is I'd like to set the stage for a discussion of how quantum mechanics relates to the themes of this weekend, the themes of personal and divine agency. Because quantum mechanics has certainly been in history the most discussed scientific theory relative to these subjects. The main claim being that somehow quantum mechanics enables a more robust view of human agency in the world, and of course if one believes in a divine being as well, that would also open the room for possible divine agency. Now, the way I'm going to approach this is the overall theme. There will be lots of details to come, but the overall theme is there are two extremes that I would like to avoid here. So the one extreme is many people have claimed that you can see an agent in quantum mechanics. So quantum mechanics, they claim, is the physical theory where you actually see the agent making choices, so to speak. And I'll say more about that in just a minute. That's one extreme. The other extreme is to say all of this talk about quantum mechanics having a special relationship to agency was mistaken, on the wrong track, and in fact, quantum mechanics has nothing to do with agency. And in fact, if you interpret quantum mechanics in the right way, then it looks just like classical physics, maybe with some strangeness like non-locality. But this is a view that's become more popular in the last few decades, and I also will argue that that view is not the right way to think about things. Okay, so here's how I'll proceed. I'm going to start by laying out two possibilities for where you can see an agent in quantum mechanics. Then what I'll do is I'm going to, without argument, I'm going to explain, well, I will give a bit of an argument, but I'm going to explain why the first way of seeing where the agent is in quantum mechanics doesn't do justice to the way the theory actually works. Then I'll go on and backtrack a little bit. Now, of course, we only have not many minutes here, and of course, to really understand quantum mechanics takes a lifetime, if not more. But I'll take some time to just lay out some of the facts about quantum mechanics that defy that sort of naive understanding that I'll be criticizing. And then I'll push in the direction of a more sophisticated understanding of the role of the agent relative to quantum mechanics, but leave it open at that stage. I'll freely admit that I don't have the final answer to how this all looks, but that will be a good place, I think, for the panel to begin a discussion of these issues. Okay, so starting then, and I will be just using chalk. This is so as they say, it's the worst time of all. It's, PowerPoint can be very soporific, but of course at 4:30 p.m. on Saturday afternoon after a day full of talks. So I'm going to try to keep myself awake, and hopefully you too, by interacting a little bit with the chalkboard. Okay, so let's start with a basic picture that informs a lot of the understanding of what's going on with agency in quantum mechanics. Now, as is typical in physics, time flows up the chalkboard, right? So here we have history moving along in its direction along the chalkboard. And then let's say we perform some quantum mechanical experiment. So for example, we send a silver atom through a Stern-Gerlach magnet. And there's this amazing fact discovered in the early 20th century called the special quantum two-valuedness, where there's only two possibilities. It either scatters upward, or in this case, to the left, or to the right, and never in between the two. There's two possibilities. Left, right. And so you think of this as time ticks forward. This is some sort of choice point. Okay. Now, before we go further into the physics involved, already just this looks very convenient for a view of libertarian free agency, because you think, well, here's what might happen. Is maybe that's what's going on in my brain. So I decide, will I take the roast beef sandwich or the turkey sandwich for lunch? I'm looking, and then there's the moment where there's freedom, and I either put my hand to the left or my hand to the right. So that sounds really nice. That sounds like, aha, there's the agent in quantum mechanics. Okay, but before we go any further, there's a qualification. So immediately some people will object and say, look, if you think that's what's going on, if there's libertarian free agency at this point, what if physics missed a beat there? What if actually, in my brain, something back here that we missed in our description said for sure, I'll go to the left? The hidden, say the hidden turkey variable that says I'll choose the turkey sandwich, but physics somehow missed it. Physics was incomplete. So there was a hidden variable. And of course, as you know, this was Einstein's initial thought about quantum mechanics, is when he heard there's nothing in the physical description of the world. There's no fact about that thing that determines before this time whether it will go left or right. Einstein said, well, physics must have missed something because the world can't be like that. There has to be a reason why it will go one way or the other. So that would be having a hidden variable. So that was left open for a long time until there were arguments put forward by people like John von Neumann to say, quantum mechanics can't be supplemented by hidden variables. It's not just that the physics as we have it has missed something. The physics as we have it is incompatible with being supplemented by further facts in the past, and so this indeterminism is real. There's nothing in the past that determines it. So let's take this now, let's take it at that stage, and I'll say this is the level of understanding of the physics that's informed many of the discussions of agency in quantum mechanics. We're sophisticated enough to say it's not just a hidden variable. That is, it's not just apparent indeterminism. We're sophisticated enough to say that there's a real indeterminism. And then the bad tendency that I'm going to be arguing against is to then not study the physics anymore and just to run on and build a theory of free agency on this picture. But everything I'll say in the next 20 minutes or so will show that this is actually a completely misleading picture about what's going on in quantum mechanics. We have to have a much more sophisticated view of what's going on here. Okay. So, just as a foil for what's going to come next when I start talking about quantum mechanics, let me just talk about a theoretical possibility. A theoretical possibility that's consistent with everything I've drawn up here is a purely classical stochastic theory. So it's possible to describe the world in a purely classical way, and you'll understand when I say classical, first of all, it just refers to classical physics, so it's just the history of physics. And I'll say more in just a few minutes to say, here's the characteristics of classical physics. But this picture is consistent with the idea that the world is classical and yet indeterministic. By classical, to fill in the details, here's what I mean. Suppose you took a snapshot of the world at a time here. So suppose you just took a snapshot, it's like a plane going through here, and you said, what does the world look like? Forget about time and change over time. Everything I said here supposes that the world looks like you would expect it in classical physics. There are things, and they have properties, they're arranged in certain ways. You can give what philosophers sometimes like to call a state description. Describe reality as it is at that time. So the story as I've told it is consistent with the idea that the state descriptions at a time are purely classical, only they're indeterministic. So the future is not determined by the past. Well, here's the news. I can't justify this with a rigorous argument. There's not time today. But quantum mechanics is inconsistent with the idea that there are classical states at a time. Quantum mechanics is not consistent with the idea that the world at this fixed time was the way classical physics described it. It just happened to be indeterministic. That's not consistent with quantum mechanics. Okay. So let me give you a slightly more accurate picture, still though using pictures. This is what they call a toy model, and yet it's accurate to the physical details. Suppose we have two boxes side by side. Again, leaving out all the details about the physical makeup of these, but suppose that we have some physical object, so suppose it's like a marble or something like that can go in one of these two sides. Okay, so suppose that it's here, and we'll call this state left, and call this state right. Okay? Now this is just like we have above, so to speak, so we could imagine that what happens is at a given time, maybe we know at time 0 it's in the left side, but we don't know in the future whether it will be in the left or the right. And in fact, the laws of physics don't determine that. That's the sort of classical stochastic picture. But let's now add the special fact that quantum mechanics puts into the mix. Quantum mechanics says, besides the states left, right, there's a third state. I'll just draw it like this. You know, leaving aside all the fancy symbols that people in physics usually like to throw at you to confuse you, right? So of course they would usually like put angle brackets around this, right? They would do something like that. It's just to make you feel like you're inadequate, right? Okay. Here's a new state. Now, for those of you who actually have done quantum mechanics, you think, what state is he talking about? It's the equal weight superposition of the two. So really you have 1 over square root of 2, these two, but I'm simplifying. What is this state like? Well, the fact of the matter is, if you open, so this is the way this really happens, and I'll have a lot more to say about, well, not a lot more, not time, a bit more to say about this in a few minutes. You have to remember that quantum mechanics is a theory in the first place about things that you don't directly perceive. And don't believe anyone who tells you that it is about things you perceive, because we don't know how to apply it to things that you perceive. People are trying to push it up toward a more macroscopic level, but it's not there yet. So here's the idea, is whether this thing is here or here, left or right, is not directly evident to you. You have to open the box, so to speak. That's just a metaphor. So you'll read that kind of thing in Scientific American. They talk about Schrodinger's cat in a box, and they say you have to open the box. Really, that's a metaphor for the idea that you have to make a choice to see whether it's in the left or right side. The world will not come to you and present itself to you saying, I'm in the left or I'm in the right. Okay? So you have to choose. I will go make a measurement, whether it's in the left or the right. I'll look, and here's the fact. When it's in this state, half of the time you look, it will be in the left. Half of the time you look, it'll be in the right. Okay? And it's natural to think half of the time before I looked, it was in the left, and half of the time before I looked, it was in the right side. It's a natural thing to look, but that's hidden variables. Okay, so we're starting now to get onto the deeper mystery, because notice what I just said. It's not that it's in the left and then maybe goes to the left, stays in the left, and maybe goes to the right. What I said was, and if it defies expectations or understanding, it's because that's just the way it is. When it's in this state, it is not in the left. It is not in the right. Where is it? The theory says there is no answer to that question. Okay, so what happens when you look? So I'm working my way up here to a more sophisticated understanding. But now we've moved past the naive view where we just have things are in a classical state and then they transition in an indeterministic way. Quantum mechanics is not like that. We dismissed that a few minutes ago. Now we're at a slightly more sophisticated understanding. So now we say, aha, before you look, when the world is in this state, it's neither in the left nor the right. When you look, and then people use a big word here, a word that sounds dramatic. They say you collapse the wave function. Okay, and so then the picture you get, and this was a picture that many people, early pioneers of quantum mechanics, sort of had in mind. Hint, in a few minutes you'll see that's not right either. But the picture you now have is before you look, when the world is in this state, reality is in this sort of amorphous, there's no reality. The particle, the marble, is not on the left or the right. It's sort of nowhere. And so this is what prompted, so this was a view that was occasionally, so let's be honest and say the early pioneers of quantum mechanics, they were pretty good at being provocative and trying to be philosophical, but they weren't always very coherent and consistent. And so they would say stuff like this to get people excited. And then Eugene Wigner, as you know, so again, we're moving toward a more sophisticated view. And this is something that I have sympathy with, but it's not quite right. Wigner said, this is where you find the agent in quantum mechanics, is you need something coming outside of the physical world to push the physical world into a definite state. But before the agent comes into the picture, the world's not in a definite state. And so this looks like, and some people are quite happy with this upshot, this looks like a kind of subjective idealism, a new kind of quantum subjective idealism. The world's in no definite state until I open my eyes, and then it collapses the wave function. Now, John Bell famously, the physicist John Bell famously mocked this view, and his mockery is repeated again and again by contemporary philosophers of physics who make their living trying to do a better job. Bell said things like, well, so when did the universe start to exist as we know it? When was the first observer in play? Did the observer have to have an advanced degree to understand in order to collapse the wave function? Could it have been an animal? Did it have to have consciousness of a human form? So these are all stupid questions, right? Questions that make you think something really fishy is going on here. And of course, some opportunists, which again I don't recommend in this case, they say, aha, so what you need is you need a super observer, some sort of deity. But that's a cheap solution. Okay, this is not a solution that's really dealing with the problem we face. But let me show you something, a deeper problem here, to show you again that this is not where we should find the agent, I don't think. Because the most people who've continued this line of thought, that when you make an observation, you collapse the wave function, they noted that there are ways to make that observer not a conscious thing, but just some special kind of physical thing. So some perhaps larger physical thing. So the problem, it seems to be, there's a systematic problem here, is whenever you want to put the agent in your theory, the agent becomes replaceable with some other physical thing that bears the same features as the agent has. That has the same properties, physical properties as the agent. So what's now called, for example, the GRW interpretation of quantum mechanics, Girardi, Ramini, and Weber, says, yes, Wigner was right. It's just not a consciousness. It's something that is constituted out of many particles. So you can see, I don't think this is where we should find the agent in quantum mechanics. Let me mention one other proposal you'll hear that also is not right, and I'll explain why it's not right. The other proposal you'll hear now is what happens. So suppose you don't want an observer to collapse the wave function. Suppose that sounds crazy. As some people would say, it's inconsistent with the laws of physics as they're written down. So what you say instead is what happens is when you look to see which side the marble is in, left or right, you yourself become entangled with that system and you split with it into two different worlds. There's the world with the marble on the left, there's the world with the marble on the right, and so then it actually starts to look like this again. Because when you do this observation, you collapse the wave function, there's the two outcomes, and so this is the multiple, many worlds hypothesis. This, in particular, is the way that Bryce DeWitt. So Hugh Everett, people have discovered in the years since Everett put forward the many worlds interpretation that he had a very weird view, and it doesn't really match quite what people say about splitting of worlds. But Bryce DeWitt, this is exactly what he said. He said, when you make a measurement, the world splits, like this. Okay, this is also not quite right, and here's the reason. So this is the key. So I know for some of you who aren't, your background is not in physics, not in quantum mechanics, there's too much here to really take on board at one go. But if there's one thing you take away, here's what I want you to take away from the technical side. This state, when you're in a superposition of left and right, is not really an indefinite state where the world, we don't know what's going on. So let's remember, so it's very tempting because we are, human beings for some reason, are very location-centric. The physical quantity we seem to like the best is position in space, as noted by people like Descartes, right? So although there's all these other quantities like energy, momentum, and now we think things like spin, still we're obsessed with where things are. And so when I draw this picture for you and I say the thing is left or right, and then I say, but what if it's in a superposition of left and right? You go, wow, that's crazy. The world can't be like that. But now here's where it gets, on the one hand, easier to swallow, and on the other hand, a bit more strange. This state of being left plus right is what it means to say the marble is sitting still. It's not moving. There's another state. It just looks a little bit different. It's the state where the marble is moving from one side to the other. Now, I'm oversimplifying greatly, but this is exactly analogous to, so you've heard about the uncertainty principle. If you know precisely where something's located, you don't know its velocity, its momentum. Vice versa, if you know something's momentum, you don't know where it's located. The correct way to understand that, first of all, is position, and I'm just going to say velocity, even though really the technically correct one is momentum. Position and velocity are conjugate quantities in quantum mechanics. That does imply that you can't know both of their values simultaneously, but I'll say a much stronger thing is true, and I'll stick by my guns with this because I know the mathematical facts that justify this claim. No system can simultaneously possess a precise value for position and a precise value for velocity. If you're in a state of, for this marble, if you're in the left, if your state is L, then you are not, so let's call this stationary, call this moving. If you're in state L on the left, you're neither stationary nor moving. Okay, what does that mean? Right? Again, it's the same thing. This is symmetric. Position and velocity in quantum mechanics are completely symmetric. The reason we get uptight about position is because position is so manifest to us. But the fact is, the state of superposition left plus right is not an indefinite state. It's a definite state. It's where you know for sure that the thing is sitting still. Let me give you a way to make this a bit more intuitive. Suppose we rigged things up so that when the box was closed, it was glowing when the marble was moving, or suppose it was very hot when the marble was moving, and it's not glowing or cool when the marble's stationary. So here's what happens is if you look at the outside of the box and you see that it's glowing, then you've destroyed your knowledge of whether it's in the left or the right. You can't know both at the same time. To have the box closed, for it to be glowing or for it to not be glowing, you can't know whether the thing's on the left or the right. And then here's the fact, is if you know, if you look inside the box and see it's on the left, then the box is neither glowing nor not glowing. So again, it's a bit of a puzzle, but that's the state of affairs that we face. So here's the fact. Every quantum state, so if you ever hear anybody say, that's a strange state, it's a superposition. Every quantum state is a superposition of some other states. Let's draw one picture to show you for the mathematically inclined, and then leave that alone for the time being. This is what it actually looks like in the abstract state space of quantum mechanics. So this is not physical space, this is how you mathematically represent the states. Is here's left, here's right. Here's left plus right. Here's left minus right. You see this is a superposition, this is just vectorial addition. This is a superposition of these two. This is a superposition of this and minus this. Now, if I've written this correctly, which I'm sure I probably have, being here in front of the chalkboard where brain IQ lowers about 20 points. You're this close to the chalkboard. But the fact is, this state is also a superposition. Let's see, actually, maybe I did get it right. I did. Look, so if you take this and add this, you get this. So left is a superposition of these two. Every quantum state is a superposition. It's not weird to be in a superposition. You cannot not be in a superposition. Okay. So, let me back that up. So, the fact that every state is a superposition, you can just see it there. But let me back up what I said just by pointing at a fact that you should know about. So I mentioned earlier about hidden variables. Okay, so the typical way people talk about the no hidden variables theorem is they say, it was proven that the future state of a quantum system is not determined by the past state. We can strengthen that now. And so I'll state the no hidden variables theorem in the form given by Simon Koushin and Ernst Specter. And here's what that says. So the difference here, the difference of emphasis will be, it's not about dynamics, it's about kinematics. It's about the way things are right now at one time. The Koushin-Specter theorem says, if you take all of the statements that you could possibly make about a quantum system, what are those statements? Things like the marble's on the left, the marble's on the right, the marble's stationary, the marble's moving. Take all those statements. Now do what philosophers do. So some of you who've taken philosophy courses, maybe elementary symbolic logic, and you write down a truth table, right? You write down T's and F's beside all sentences. What else do you have to do though, right, is you have to obey the rules of logic. So if you assign true to one proposition, true to another, then you have to assign true to their conjunction, of course. The conjunction of two true statements is true. So here's what the Koushin-Specter theorem says, is take all the propositions about a quantum mechanical system, go start assigning trues and falses to them, always following the rules of logic. You can't do it. There is no consistent assignment of trues and falses to all the statements about a quantum system. So what does this mean? The simplest answer, I mean, there is much more metaphysical thinking to be done about this, but the simplest answer is many of those things, that properties we could attribute to a quantum system, are neither possessed nor not possessed at a given time. Now, one way to see this, a way that I'll sort of suggest, but this is an old idea, it's the idea of complementarity from Niels Bohr, is the best we humans can do in describing a quantum system is pick a subset of the set of all propositions and consistently assign trues and falses. Others of the propositions, if we want to be consistent, we have to ignore, because we'll fall into inconsistency if we try to assign trues and falses to all of them. Okay, this is also consistent with another fact. So I mentioned earlier, and this is just another idea I want to get on the table before I conclude, is I mentioned before, I said, so you think, let's solve this problem easily, right? If you want to know all the statements about this system here, you want to be able to assign trues and falses to all the claims, let's just go look and take a pad of paper with us and write down true and false to all the statements. So if I look and I see this marble here on the left, I write down true next to the sentence, the marble's on the left. And I go through and I just write down what I see. So it has always been thought, so at least with people like Niels Bohr, the idea was, so Niels Bohr, the way he put complementarity forward, and this is actually using, I think, the phrasing of Pauli, is he said in quantum mechanics you can't open both eyes at once. You have to open, in order to see clearly, you can open one at a time, but not both at the same time. So that's similar to this idea I was suggesting, that you can't assign consistent values to all the propositions, but you can choose a subset and assign a consistent value to them. So we now know in the last 30 years it's been proven that that's the case in terms of direct perception of a quantum system. So there's a result called the Nocloning Theorem, which if you think about it first, you think this has nothing to do with perception. I'll explain what it has to do with perception in a minute. But the Nocloning Theorem says there's no way to take two quantum systems and have them interact in such a way that the second system consistently copies the state of the first system. And by copy, I don't mean in any sense like somehow literally take it. I mean just report it with full accuracy. That's impossible by the laws of quantum mechanics. Now, as a consequence, what that means is any embodied observer, any observer whose brain is a quantum system, like hopefully us, our brains cannot reliably report all of the facts about a quantum system. So perception can't be directly veridical of any quantum system. But what we can do is we can choose a piece of the quantum state to examine. So as I said before, we can decide to open this box and look, is the system on the left, is the marble on the left or the right? And we know from experiments done in the lab that we can do this quite reliably. What we cannot do is we cannot both see if it's on the left and the right and see if it's stationary or moving. We have to make a choice between those two. Okay, so where does this leave us with respect to the agent in quantum mechanics? And now I'll make a somewhat bold claim that's not nearly as well justified as things I've said about the facts of quantum mechanics. It's more of a suggestion. The agent, I believe, is not found in quantum mechanics. You can't look in the theory of quantum mechanics and find one of the things in there that corresponds to agency. And by the way, I think that we wouldn't hope for that in any case because the goal of physics isn't to do that. Nor do I think, to make the statement even stronger, do I think you see in quantum mechanics the physical things that underlie agency. I think that's also not present because there's nothing, I think, in the actual theory that suggests that you see agency. Does this mean, so one possibility, and this is a possibility that many interpreters of quantum mechanics are aiming to achieve, is a world ultimately where agents are superfluous. So that's certainly the way many people see classical physics. Many people see classical physics as describing a world in which agents are superfluous. They maybe emerge in some way, but they're not integral to the story. The hope of many was with the advent of quantum mechanics, the agent becomes a necessary internal part of the theory. You look inside at the way it reports the world is like, and you see there's room for agency, or there are agents. I've hoped to indicate here that that's, I don't think, the case. But that doesn't mean the agent is superfluous in quantum mechanics. The agent isn't in the theory, the agent is the user of the theory. The temptation with classical physics is when you use the theory, you don't realize you have choices to make when you use the theory in classical physics, because it's as if once Newton produced his theory, it was a template that you could just go and set against the world at any place. Your role wasn't really important. You didn't even need to be here. The Newtonian theory just mirrors the world. That's the picture we get. Now, the way I've been trying to put forward quantum mechanics, which is very much against the way many people are trying to develop, say, the Everett interpretation of quantum mechanics, the developers of the Everett interpretation want to make the theory like that again. They want to say quantum mechanics just looks like the world looks like. It's a mirror of the world. But if you take the Bohr idea of complementarity seriously, which many people don't like to do because they see the implication that I'm trying to press here, is the theory as it's given to you doesn't tell you what the world is like. You have to use it to find out what the world is like. You have to choose what to measure. Now that's overstated a little bit because people think, okay, that's operationalist. Let me rephrase it. You have to choose what you want to describe. No choice made by you, no description is made by the theory. So what I'm putting forward as a suggestion for discussion is that the agent is not inside quantum mechanics. On the other hand, quantum mechanics does not make sense as a theory of the world unless it's used by an agent. Thank you.